several decay processes in nuclear phenomena like beta decay, gamma decay, and all this stuff. And now we have stumbled upon very interesting aspect of nuclear physics course is the nuclear reactions. So basically here you artificially bombard some nuclei with another, and some interaction between those two nuclei at this particular momentum takes place, and something very interesting happens. Now, how to study that interesting phenomena? Now, always these sort of things are going on inside stars, okay, and at high temperature or pressure or at different situations. So it is obviously not possible for us to go to the star and see those things. So what we do is that we try to do that same situation. We try to make that same situation in the laboratory, and then try to understand what goes on inside stars, or what exactly happens. And by studying nuclear reaction, we also can understand more about the nuclei or the nuclear properties. So this is very strong thing to do in nuclear physics, that to study the nuclear reactions. And to study those nuclear reactions, we have these particle accelerators, where we accelerate nuclei, and then they bombard on some kind of target, and then these nuclear reactions take place, and which we measure the products, and we try to study nuclear physics as a whole. So I already discussed in my last lecture that the standard nomenclature is that if there is a small a projectile falling on a capital A target, then if the product is consists of two particles, that is one light ejectile small b and one residual nucleus capital B, then the way to write this is capital A small b capital B. So this is the way that you write. Now if it so happens that there are three body final state, then instead of small b ejectile, then you write, like, as for example, there are two particles that also comes out from the small b, x and y. So you will write a small a comma xy parenthesis closed, and the capital A and capital V will remain as it is. So it is like that. And we have discussed that q value can be given by this expression, that like you may be given some nuclear reaction in the examination, and then you might be asked that what is the q value of this reaction. So then what you have to do is q value is equal to, as you can see from this expression, that is the difference in the rest masses of the nuclei minus the excitation energies of those nuclei. Like it may be that these small b and capital B, the particles that are ejected in the exit channel, and they may be excited as well. So if they are excited, that energy has to be also taken into consideration. And you already know what is the center of mass energy. So you can just transform, because you do the experiment in the lab frame, but to understand anything, we have to go to some standard frame, which is a center of mass frame. So you can convert that lab energy, which is the beam energy, E beam, that you can convert it into center of mass, right? So you can get the value in the center of mass, and then you can conclude about the properties in that center of mass frame. And another interesting thing is we cannot measure everything, right? So what exactly we can measure? So we can measure the Z and A, that is the charge number and the total number of nucleons in a nucleus of the emitted particles. And also, since we are putting in detectors at particular locations, so we know at what angle we have put in the detectors. And if some particles fall in that detector, so we can obviously know the angle at which the exit channel particles have fallen. And we can also measure the energies of those particles, because those particles will fall on, say for example, on a silicon detector. So you know from Bethe-Bloch equations, if a charged particle falls on, say, a material, so what will be the energy loss? So we will measure the energy loss of that particle. So technically speaking, when the particle falls on the detector, it will slowly lose energy until it stops. So if you now just measure what is the accumulated energy, so that is the energy with which that particle has fallen on the detector. So we can measure the energy of those detectors. Now you might ask that if that particle does not stop. So that is another interesting issue. The detector might not be, that is, the material might not be thick enough to stop the full energy of the particle. Then that also we can actually see from the spectra, that how much energy it has deposited. Okay, from there we can actually calculate with what energy it has been emitted during the nuclear reaction. So we can measure the energies and the angles, and we can measure the cross section. So at a particular solid angle, how many number of particles have fallen, provided you know the beam intensity, that is what is the total number of particles that is incident on the target, and what is the total number of particles of a particular type that has been scattered at a particular solid angle. From there we can measure the cross section. So that cross section, that will, now if you plot the cross sections at different angles, so you come out to a curve. So it is like d sigma d omega versus theta. So in the x-axis you plot the angles, and at particular angles what are the number of particles that have fallen in the detector in that particular solid angle. So that will give you the cross section. So now for particular nuclear reactions, these cross sections will have definite shapes. Okay, so if there is angular momentum transfer L is equal to 2 in that particular reaction, it will have a particular shape. If it's L equals 3, it will have a particular shape. So from there we can actually determine in the nuclear reaction what is the angular momentum transfer. That will also help us to study the nuclear structure. So how was the nucleus actually there in the original nucleus? From the nuclear reaction we can study what exactly has happened. So that will help us to study all the nuclear properties. Also we can say whether what is the orientation of the spins. Now this is will be a slightly difficult experiment, because to study the orientations of spins you have to make a polarized beam, not an unpolarized beam. With unpolarized beam you can measure cross sections, how many particles have been ejected in a particular angle. But to study the orientation of spins you have to have a polarized beam, that is a beam of particles whose spin is oriented in a particular direction. Now then, like you have studied that beta decay, this experiment which led to this Nobel Prize and all that stuff. So you have studied that you
Yes,
could
sir.
orient, yeah, you could orient the spins of the particles in a particular direction, and then you can conclude what has actually happened. Now, if you heat them, then this spin orientation will be destroyed. Then it will become again an unpolarized beam. So to study the orientations of the spins, you will require a slightly difficult experiment which requires a polarized ion source. So you have to have a polarized beam incident on a particular target. So we will not discuss about these polarized beams because that does not come under the purview of a general nuclear physics course. So have you all could arrive at that rate 0.30 per minute from this formula? Have you tried it at your home from this expression? So unless you do it, you won't have a feel what exactly is the cross section. You have to,
Yes, sir. Yeah,
because
yeah.
yeah, so you could get that 0.30 per minute. So that actually is a rate. So that rate, with that rate, that number of particles, that is per minute 0.30. So approximately you can say in 3 minutes one particle will fall in that particular solid angle, right? Now if you increase the solid angle, you will see the number of particles falling will be more, right? Because cross section is constant, right? And at that particular location, at that particular theta, that is constant. So if the rate if your delta omega increases, solid angle increases, that your rate will increase. But at the same time, if the solid angle increases, then you will lose your resolution. Then you cannot definitely say it falls in 12.1 degree or 12.2 degree. So you can approximately say it falls within 12 to 13 degrees. So it is like that. Do you get my point? This last point that I said, you will lose the
Can you
resolution.
repeat the last point, sir?
Yeah,
As you
yeah.
said
So
that for a, if we increase the theta, then we say that number of
no,
particles.
not theta, not theta. We are not increasing the theta. Theta is at a particular theta. At a particular theta, that solid angle is there. So that delta omega is actually the opening of the detector. So you consider that the detector cross section is delta omega, right? So
Acha,
that
okay.
detector opening, that is the detector opening. Now if I increase the opening of the detector, Say for example, instead of delta omega, the detector subtends an angle of twice delta omega at the target. So if the solid angle is more for the detector, so then the rate will be more, that is more particles will fall because the detector is bigger detector. So if it's a bigger detector, more particles will fall on that detector. So that will give, if the solid angle is more, the rate will be more.
Acha,
Do you
acha, now I
understand?
got it. Yeah, yeah, yeah.
So,
It's
so
all
part meaning,
depending upon the area of the detector,
yes,
sir.
yes, the
Okay.
opening area of the
Yes,
detector. But
yes, yes,
if we increase the area of the detector, then what happens? You lose the resolution, because now the delta omega is small. So you can say definitely that the particle falls between 12.2 degree to 12.4 degree, say. But if it's increased, then you cannot precisely say whether it falls in 12.2 and 12.4. You might be able to say it falls between 12.2 and 12.8, but not between 12.2 and 12.4, because if the area increases, then it is more difficult to specify where exactly that particle has fallen. It is
yes,
somewhere fallen between 12.2 and 12.8, but you don't know whether it falls on 12.4 or 12.6. You don't know. You know it falls within 12.2 degree and 12.8 degree. So that's why I'm saying the resolution reduces. Now do you get it? The resolution, reduction of the
yes, sir.
resolution. You cannot
Sir,
pinpoint.
what parameters we have to think to fix the theta lab?
What?
Sir,
Which
how we
parameter?
fixing the theta lab? I mean, what
Okay,
parameters
okay. So
were?
so see, now the issue is, if you have to have the complete measurement of the angular distribution, so you have to, best thing is to, you have to put as many detectors covering all the angles, right? But there might be geometrical constraints. The detector itself might be 2 centimeter thick, then you cannot put within 6 centimeter, you can at most put 3 detectors. So those 3 detectors, they have a particular detector opening, say 5 millimeter each. So if you put it like that, so it might be so that you are getting the measurements at an interval of say 3 degrees. Okay, now if you put in better detectors, you might be able to get the cross section maybe at an interval of 1 degree. Even even after that, if you put in even better detectors, you might be able to get the cross section at an interval of zero point 0.1 degrees. So issue is how accurately we can measure it. So that will be that if you can measure all the angles say at an interval of 1 degree, then your resolution is 1 degree. If you can measure all the angles at an interval of zero point 0.1 degree, then your resolution is zero point 0.1 degree. So the
Okay.
more the better, the more the better. But obviously
Yes, sir.
there would be geometrical constraints. You cannot build such detectors that you cannot just go on reducing to the to the atomic size, right? You cannot go to angstrom level. I mean, obviously it's not possible like that way. There are other ways
Yes,
to do it. Yeah, other ways, and that might be gas detectors, multi-wire proportional chambers, where you can measure with even much where exactly the particle has fallen. You can, main thing is that in a nuclear reaction, when the particles are emitted, how accurately and with the most I mean the best resolution, how you can measure it. Because if you can measure it with a good resolution, when you try to theoretically analyze that reaction, then you can fit the curve better. Basically you have to fit the d sigma d omega versus theta, what is the angular distribution. Okay, so basically there will be theta in the x-axis, and in the y-axis there will be d sigma d omega. So you are actually saying how many number of, in essence you are saying how many number of particles are falling at a particular angle. Okay, now this will change
yes,
over different angles. So at 2 to 3 degrees, that number of particles falling will be different than at 60 to 65 degrees. It will be totally different. And once we analyze that, then only we can tell anything about the nuclear properties. Why it is high number of particles emitted in the forward angles, and why it is low number of particles in the backward angles. So these are different things that you can conclude. So the best possible thing is, as many, I mean, with the best possible resolution, you measure the angular distribution. So you put detectors in a most judicious way that covers more or less the angular distribution from say 0 to 180 degree. Okay, then you have a total grip on the how the nature of the angular distribution changes from lower theta lab to higher theta. Now once you have all the theta labs, then you convert them to the theta cm. Then the ideal thing is that in the theta cm plot you have the full coverage 0 to 180 degree. Okay, so that will help you. Okay, now another interesting thing is the impact parameter in a nuclear reaction. Now you can see this red ball, which is a beam particle. So one particle, so I actually I drew it as a one particle, but actually you will see there are thousands of particles falling on a target. But to make you understand, I plotted it as a one particle beam. So it is coming and going to interact with the target. Now you can see the impact parameter, that is actually the perpendicular distance between the center of the target nucleus and the trajectory of the beam particles. So can you tell me what will be the situation when the impact parameter is very big and what will be the situation when the impact parameter is very small? Can you tell me what will happen?
It will be head-on collision if impact manometer is very low,
Yes,
and
yes.
if it
So
is high, then it will be scattered.
yeah, so that means if the impact parameter is very low, that particle will be scattered by a very large angle. It might even
Yes,
backscatter. It might go just, you have seen it in Rutherford scattering. It might even backscatter. But if the impact parameter
yes,
is very high, it will be less scattered. So it will be scattered by say 20 degree. But if the impact parameter is very low, it may scatter by say 150 degree. Right? So that actually defines the impact parameter. Now we can choose the n and the z for the beam, right? Number of nucleons and the charge number of neutrons and number of protons of the beam. NZ of the target also we can choose. And the energy of the beam also we can choose, but nothing else. We cannot choose anything else. What will happen? We don't have any control. After the reaction, what will happen, at what angle it will scatter, we don't have any control on that. But what we have a control is that we can fix which beam we want. We can fix the number of neutrons, number of protons of a particular beam. Like if I want a lithium 7 beam, so we know it has got 4 neutrons, 3 protons. If we want a lithium 6 beam, we know it's 3 protons, 3 neutrons. If we want a beryllium 7 beam, we know it's 4 protons, 3 neutrons. And for a target, if we want a carbon target, we know it's 6 protons, 6 neutrons. If we have a lead nucleus, we know it's 82 protons, 126 neutrons. But we cannot choose anything else. And also the energy of the beam we can choose. We can tell it, we can make the beam to be 35 MeV, we can make the beam to be 42 MeV, we can make the beam to be 2 MeV. We know it. Depending on what actually we want to study, we can choose the beam energy. If it's very high beam energy, it will be direct reactions. If it's a lower beam energy, it will be compound nuclear reactions, like that. Okay.
yes,
Now,
sir.
yeah, and another parameter is the Coulomb barrier. Okay, so when this beam particle is coming to interact with the target nucleus, now both these nuclei have protons. So, like Z1 for the projectile, Z2 for the target. So you know that since these are charged particles, so they will be interacting with each other.
Hello, sir.
All of you can hear me?
Hello,
All
sir.
of you can, yeah, all of you can hear me?
Yes, sir.
Yeah, so somehow what happened, suddenly this screen went out of my computer. So I have again put this. I don't know why this happened. Anyway, can you see the screen?
No, sir.
Okay, then I have to again present. Oh, yeah. Can you see it now?
Yes,
Yes,
sir. We
sir.
can see.
Okay. Okay. So another parameter is the Coulomb barrier energy. Okay. So as I say that since the beam particle and the target nucleus both have positive charge due to the protons, so there will be repulsion. That is, and that will form a barrier kind of thing. So basically it will repel the projectile so that this projectile will be decelerated. So when it is incident with a particular momentum, and it's approaching the nucleus, so since both in the projectile and both in the target, both in the projectile and the target there are protons, they will repel. Okay, and this repulsion is thus the Coulomb potential. You can just calculate Z1 Z2 by R. Now this 1.44 comes out due to the energy unit that is given, MeV Fermi energy unit. If you put it, that will come out to be 1.44. Okay, so you can calculate and verify, that will come right. The epsilon naught 1 by 4 pi epsilon naught and Z1 Z2 by R. If you take it in MEV, that you see the wallet card that I told in the first lecture itself, that if you use the wallet card there, you will see that 1.44, that number will come if you use this as in MEV Fermi unit. It is very easy. Okay, so this Coulomb repulsion will result in a Coulomb barrier. Now, if the energy of the incident projectile is less than the Coulomb barrier, like if the Coulomb barrier is 35 MeV and you make a beam energy of 20 MeV, then this particle will not be able to see the nucleus, right? Do you understand what I mean? Do you understand what you mean?
No, sir.
What I am saying, since there is this barrier, right? This is a Coulomb potential, so it is a positive barrier. You understand? It's a positive barrier,
Yes.
like in quantum mechanics. So I am saying that this between this projectile and target, the Coulomb barrier is 35 MeV. Now you are given a 20 MeV beam. So with the 20 MeV beam in the energy scale, so if you plot the energy in the y-axis, what will happen? This beam energy of the projectile will be lower than the Coulomb barrier. Coulomb
Yes,
barrier
sir.
is 35 MeV and your beam energy is 20 MeV. So if there is a barrier, so it cannot actually see the nucleus on the opposite side of the barrier.
Yes,
Do you
sir.
understand? Like a Chinese wall. So if you are
Yes.
below the wall, you cannot actually see what is actually going on inside the wall. On the other side. So here also it's like that. So if it's then only mostly its Coulomb interaction will happen. It will not be able to see the nucleus, and so no nuclear interaction will happen between the projectile and the target. But if you have a beam energy
Yes.
of say 40 MeV, so it is above the barrier, so it can actually see the nucleus on the other side
Yes.
of the barrier.
Yes.
So then
Yes.
there will be nuclear interaction. Now what happens?
Correct.
So mostly you will see with lower energy incident projectiles, mostly you will see Coulomb interaction, mostly Rutherford scattering and all that stuff. But
Yes.
once you increase the energy, you will start seeing nuclear interaction. Now in Rutherford scattering, there is Coulomb interaction we can deduce analytically. You have an analytic expression. So it is very easy to calculate. We also use this during our experiments to calibrate. But with nuclear interactions, you don't have an analytic expression. It is difficult. So you have to trial and error, you have to do it. As I said that there is so much of intellectual effort gone into nuclear physics, understanding the nuclear force, but still we don't know exactly what the nuclear force looks like. So we are only doing approximations over and over. We are doing, improving on our approximations, but we don't have an analytic expression like the Rutherford scattering, right? And also this R, you have this Coulomb energy Coulomb barrier energy 1.44 Z1 Z2 by R. This R is in Fermi. And this R can, you also refer to my lectures in the first few lectures, that R can be written as 1.2 times a to the one third, where a is the mass number of the any of the nucleus. So here
Yes,
this
sir.
R is actually the distance between the centers of the projectile and the target. So basically it is the sum of the radii of the projectile and the target. So for the projectile it is 1.2 a to the a1 to the one third, and for the target it is 1.2 a to the a2 to the power one third. So if you just sum up, right, if you just sum up, that will give you your R, small r. So R is about equal to 1.2 a1 to the one third plus a2 to the power one third. Okay, now what are the different types of collisions that I was discussing with different energies, right? Bigger energy, lower energy, mid energy. What are the different types of collisions? So if there is a very close interaction, impact parameter is very low, you will see the bottom figure, there will be compound nuclear reaction, right? So this projectile will be absorbed by the target, so it will make a compound nucleus, and then it will start emitting particles, neutrons mostly, and there are other fragments. Now the time scale is very slow, about 10 to the minus 20 seconds. Now if it's the impact parameter is larger, so it will be less scattered lower by an angle, and it will hit the target, and there will be some particles emitted, but it is not a compound nucleus formation, it immediately takes place. So it is a very fast reaction, direct reaction. So you can see it will be 10 to the minus 22, even 10 to the minus 23 seconds, right? So it will be
Yes, sir.
1,000 times faster than a compound nuclear reaction. So if you see the angular distributions, that it's written sigma theta. Sigma theta is actually d sigma d omega. So basically it is the cross section which depends on, it's a function of theta. So you plot d sigma d omega versus theta. So if you see it, you see that theta cm, as theta cm increases, the uppermost figure, as theta cm increases, the cross section reduces. You can see it, right? The cross section reduces. In the lower theta cm, the cross section is very high, that is many number of particles are scattered at that particular angle. But if the theta cm increases, you see less number of particles emitted in that particular angle. Is it clear? The first figure, topmost figure,
Yes.
theta cm versus. Now the lowermost figure is that of a angular distribution for a compound nucleus reaction. Now in compound nucleus reaction, what happens? First the projectile is absorbed by the target, and then its previous history is lost. So the compound nucleus does not actually remember what was the target and what was the projectile, so it becomes a compound nucleus, right? It's something like, uh, as for example, if you have in your childhood, you have played with play-dohs, right? You
With
have
what,
played
sir?
with play-dohs, the colored clays.
No, but I same them. Yeah.
Yeah, I mean there are different colors of clays that are available, and with those clays you can make different models and figures, right? My daughter currently does that. So you have
Yes, sir.
like red colored clay and blue colored clay, so if you mix them it becomes a violet colored clay. You can make some doll out of it. Now in a compound nucleus, what happens, that red color and blue color mixes and becomes a violet color, and that violet color does not remember who was red, who was blue, and whether red and blue mixes up to make violet or what, it doesn't remember. Okay, so that actually is a compound nuclear reaction. So it forgets the previous history. Now once it forgets, then it emits isotropically. So you can see that this compound nuclear reaction angular distribution, it is symmetric about theta equals 90 degree. Theta cm equals 90 degree, it's symmetric. So you have a very lowermost theta cm, you have a slightly higher cross section, and also very higher theta cm, you have a higher cross section, but it is minimum at 90 degrees. Do you get the plot, the second plot?
Yes.
So that is the angular distribution due to a compound nuclear reaction, because it forgets the previous history. But for the direct reaction, that is the upper one, it is forward peaked. So it actually, it's a very instantaneous process. So it hits and some other particle goes out. Okay. So I will discuss what are the types of direct reactions that might happen. So it is forward peak means that only most of the particles are emitted in the forward direction, and in the backward direction only some particles are emitted. So these are the two different types of angular distributions, the cross sections versus the angles. So if you compare the direct versus the compound reactions, so it's a fast reaction is direct, that is 10 to the minus 22 or 10 to the minus 23 seconds, occurs with a single collision, and there is a smooth energy dependence. So there might be dp, that is a deuteron is incident and a protons goes out. There might be helium 3d, that is a helium 3 is incident and the deuteron goes out. There might be pd, that is a proton is incident and a deuteron goes out. Accordingly, you also adjust the residual nucleus because you have a target. So in case of pd, say, that means the proton actually picks up a neutron and becomes a deuteron, so the residual nucleus will have one less neutron than the target nucleus. Do you understand that?
Yes, sir.
Okay, so same for the d helium 3. So it's a deuteron is incident and a helium 3 goes out. We for simplicity, we have not written the target nucleus and the residual nucleus. You can actually write, if the target nucleus is carbon 12 in case of pd, if the target nucleus is carbon 12, what will be the residual nucleus? Residual nucleus will be carbon 11, because it picks up one neutron. The proton picks up one neutron to become a deuteron, and then the residual nucleus will have one neutron less than the target nucleus. As simple as that. And for compound nucleus, it is 10 minus 20 seconds or even more. Even it can go to 10 to the minus 16 seconds also. It is that much slower. Proceeds through many complex states in compound system, and the memory of the beam and target is lost. It doesn't remember who was the beam and who was the target. And the particles are emitted isotropically in the center of mass frame. As for example, alphas may be emitted, protons may be emitted, neutrons emitted, even heavy ions also may be emitted. Okay, fission fragments and all that stuff might be emitted. Now, what are the different kinds of nuclear reactions? First, it may be elastic scattering. What is an elastic scattering? Here, small b equals small a, capital B equals capital A. So exactly what the projectile and target is, that in the exit channel, the ejectile and residual nucleus are the same as the projectile and the target, and the nuclei are unchanged and unexcited. So whatever the incident particles, the emitted particles are also the same, and they are also not excited. So they remain as it is, they only get scattered by a particular angle. There might be inelastic scattering. Now in this case, what happens? The small b is excited small a, and capital B is excited capital A. So there will be same value of n and z, the same number of neutrons, same number of protons are there, but the products can be in excited state. Star means actually excited. There may be excitation due to Coulomb excitation, that is the Coulomb force might excite this nuclei, or there may be due to nuclear excitation, that is they may get excited due to nuclear excitations, nuclear force, excitations due to nuclear force, or excitations may be due to Coulomb force. There may be transfer or rearrangement reactions as well, that is small b is not equal to small a, capital B is not equal to capital A. That is, some projectile target combination is incident, that is some projectile is incident on the target nucleus, and some different ejectile and a different target different residual nucleus is produced. So this can be called a transfer reaction or a rearrangement reaction. So here the nucleons are exchanged between small a and capital A. So many different names are given to this type of reactions, like pickup, stripping, charge exchange, knockout. So very different names. There may be deep inelastic scattering. So what happens? This is deep inelastic. That means target nucleus is kind of excited in a very complicated way. So many nucleons may be exchanged. So once this projectile falls on the target and lots of nucleons are exchanged, and then it may actually excite the whole whole target nucleus, and then it may come out as the same original projectile. So it is kind of complicated, and the nuclei are strongly excited. And there may be compound nuclear fusion. So beams and targets fuse completely or incompletely, that is, partially or fully. There are high excitation energies and angular momenta are achieved. That is, it excites the nucleus very well because it is almost head-on collision. And the resulting compound nucleus emits particles and gamma rays to remove the energy. So always the tendency of the nucleus would be to lose energy as fast and as much as possible and return to the ground state. That is a rule of nature, that you will always try to achieve the lowest potential energy. So it will remove the energy as fast and as much as possible. And this is a particular very nice plot that I show. So if you plot it energy per nucleon means if it's a deuteron of 10 MeV, 10 MeV deuteron means per nucleon what? 5 MeV per nucleon. So the lab energy of the deuteron is 10 MeV, but if you divide by the number of nucleons, because deuteron has got 2 nucleons, so I can say that it is a 5 MeV per nucleon deuteron beam. So it is like that. So if you plot in the x-axis the energy per nucleon, and in the y-axis I'm plotting the impact parameter. Everybody can see this plot?
Yes, sir.
So now you can see, so there is this dotted line is the Coulomb barrier. So you can understand the projectile and target, the Coulomb barrier, if you can calculate simple by this Coulomb potential, Z1, Z2 by R. And that dotted line is the energy per nucleon. If you calculate in the x-axis, you plot the energy. So that dotted line actually gives the Coulomb barrier. So you can see that elastic and inelastic scattering are there. So with high impact parameter, that is, it is going far away from the target, it is mostly elastic scattering. Now if you reduce the impact parameter a little bit, it will become inelastic scattering. And that inelastic scattering may partially occur due to Coulomb force and partially due to nuclear force as well. But the impact parameter has to be slightly lower than elastic scattering to make it happen. Understand?
Yes, sir.
Okay. Now, with that particular impact parameter, because highest impact parameter is elastic scattering. Now, if we reduce the impact parameter, that is more and more interaction between the target nucleus and projectile is taking place. That is becoming closer and closer to the target. So more and more interaction. So as you reduce the impact parameter, there will be these nuclear reactions coming up, transfer reaction, knockout reaction, and these are actually fully due to the nuclear force, not due to the Coulomb force, because it is above the Coulomb barrier. Now if you reduce the impact parameter even lower, that is more complicated reactions taking place, that is deep inelastic and even fragmentation reaction, that is, it is heating with a lower impact parameter, that means it's hard heating. Hard heating, there will be fragmentation, that is, target nucleus might fragment in a number of fragments. If you reduce the impact parameter even lower, then it might have a fusion, that is, a compound nuclear formation will be there, fusion evaporation, that is, first it fuses and then it evaporates nuclei. All these neutrons and other nuclei will be evaporated, because since it is a low impact parameter thing, so it hard heats and becomes a compound nucleus, and it is heavily excited, and then it starts evaporating. Temperature increases and it's evaporating. So since it is incident at a lower impact parameter, it actually hits the target so heavily that it imparts energy to all the nucleons involved in the target nucleus. So then what happens? It becomes excited and starts evaporating nucleons. And you see the lowest impact parameter and highest energy, that will result in multifragmentation. So it is one order of magnitude greater than fragmentation, because fragmentation, there may be a number of nucleons. The target nucleus fragments into a number of nucleons or number of fragments. But multifragmentation means it is many number of fragments. So is this plot clear to everybody? All of you tell me. It is clear?
Yes, sir.
Yes, sir.
Yeah, so absolutely clear, right? Okay. So you can see how to make interesting nuclei, this cartoon. So if it's distant trajectory, then it's Coulomb excitation. So the target nucleus is almost sleeping. Doesn't matter. So if it's a transfer or deep inelastic or incomplete fusion, the impact parameter is very low, so it hits hard. Now there is fusion evaporation. If it's all very low impact parameter, it's head-on collision. So then the target nucleus is impacted heavily. And even the impact parameter energy is also high, then it becomes fragmentation. That the target nucleus fragments to a number of nuclei. Do you like this plot?
Yes, sir.
Yeah. Okay. Okay. So I will stop here. So do you have any questions right now?
No, sir. Right now, no. It was
Okay. So
very
you got.
goodly explained today.
Okay. So these are. I mean, try to form different pictures in your head. That will help you understand nuclear physics in much better way. So you are practicing. As I said, you are practicing the problems very well.
Yes,
I
sir.
said again and again, again and again, again and again, again and again. I'll just, if you just put a recurring, that is again and again, just do the problems again and again, go through the lecture notes again and again. That will do it. Practice and practice and practice and practice and practice. So you start doing it right away because your exams will be somewhere in the middle of February. That's what I was in the meeting last time, maybe a few days back, and it was discussed like that. So it will be, the exam will be around second or third week of February. I am not very sure, but I remember something said about that, that it's around second week of February. So you start practicing right away, do the problems, see the, compare the solution sets, and try to do it on your own. And then while practicing, just compare with the solution sets that I have given, and also go through the lecture notes again and again. If you have any questions, start asking me right away. Just I mean, after I finish the lecture of the day, then start asking questions. Okay, we can discuss a number of things in the next lecture. So we are almost completing the course, so maybe another one or two lectures. So you can ask questions about the problems, about these lecture notes, anything you can ask, doesn't matter. So you assemble all the questions. So I tell you one thing, that it is better to have discussions with your friends. So try to get it solved discussing with your friends. So that will, because if you can make your friend understand, then your concept will be clear also. Okay, try to do that first, and then the questions that all of you, even after discussion, cannot solve, that question you ask me in these lectures. Okay, is it clear?
Yes, sir.
Yeah, so that way you will also practice, and we will also save time, that only the most difficult questions you discuss during this lecture session. Okay. Okay, then I think
Sir,
now we
sir,
are.
one thing.
Yeah.
Sir, can you please send us the whole lecture note so that we will, I mean, copy from Xerox, will distribute, because I think it is very difficult to for this time to write down all these things. Make your own notes so that we will only refer to your notes and we will practice refer to
Yeah, I
problems.
understand. I understand. What I could do, actually, I sent the MSc lecture 2. Okay. So you already have the lecture 1, right? But part by part. So do you
Yeah, yeah,
want
yes.
again me? Yeah. So because I have already sent the lecture 2, that is starting from beta decay till the end of the lectures. Okay. And
Acha,
that
okay,
was around
then
20.
we'll do that. Okay,
I,
then
I, I
let's do
because
that.
I sent it day before yesterday, I think. So I have already sent it, and the lecture 1, I think I have given part by part, like every day is like
Yes,
4 or 5.
yes, yes,
So you
yes,
can
yes,
print
yes.
it from there. Otherwise, again, I have to I mean concat. That is that I have to add all the PDFs again and then send it. I mean, if you can already print it out, because I think 4 or 5 parts are there in the MSc lecture notes 1. So as I have given, so if you can print it from there, that's fine. Otherwise, again, I have to put the PDFs again together and again upload. I mean, it's a redundant procedure. So you can
No,
just
no,
print
we'll
it
do
out
that, sir.
from there.
Yeah,
Okay.
yeah, we'll do
So
that.
you
We'll
just,
do that.
if you face any problem, then tell me, because I have all these PDF files. I can again send it separately or upload it into a Google Meet, because it's no use again adding up all the PDFs. because MSc these lecture notes too, I have made it and send it day before yesterday, the Google link. Okay, if you face any problem in the lecture notes one, so tell me again, I will send the part by part, because again it's not good to again add up all the PDFs. It's a painstaking stuff. Yeah.
Yeah, yeah, yeah.
Okay,
We'll
then
do that. Yeah,
yeah,
yeah.
okay. So if you have any questions, ask me in the next lecture. You write down all the questions, we can discuss, because we are near the end of the lecture. I think another 2 lectures we will complete the course. No problem. Even not even two. In the next lecture itself, we will complete it. Okay. Then we can discuss. Okay. So assemble all your questions. So we will discuss last 3 or 4 lectures. We will just discuss things. What problems you have, any concepts that you want me to repeat, so that we will do in the next 2 to 3 lectures. Okay, is it clear?
Yes, sir. Yes, sir. It is clear.
Okay, okay, all of you just tell me hello and goodbye, that all of you are here still. Yeah.
Yes, sir.
Okay, you understand? Yeah, you understand everything?
Yes, sir.
Yes,
Yeah,
sir.
you understand everything? Okay, okay, so